Today we are going to learn about optimizing sliding window for real-time LLMs. We will explore how to implement and fine-tune sliding windows to enhance performance in real-time applications, focusing on maintaining model efficiency and effectiveness in processing continuous data streams.
Welcome to our session on optimizing sliding window mechanisms for real-time large language models, or LLMs. The sliding window is a crucial technique used in various computational processes, especially for handling continuous data streams. In the context of LLMs, it plays an important role in maintaining the flow of data, ensuring that the model remains updated with the most recent information while processing. Throughout this video, we will delve into how sliding windows function, their significance in real-time applications, and the optimization strategies that can be applied to enhance model performance and efficiency.
In the realm of real-time data processing, several challenges persist that affect the performance of large language models. Firstly, the velocity at which data streams can overwhelm a model if not managed effectively, leading to bottlenecks. This is often compounded by latency issues, where the time taken for a model to process and output results can lag behind the incoming data. Furthermore, resource management is a critical concern, as processing large volumes of data requires substantial computational power and memory, which can be a limiting factor. Maintaining data consistency is also crucial, as the model needs to ensure that the information being processed is accurate and up-to-date. Lastly, adapting to variability in data, such as changes in data format or content, requires a flexible and robust approach to processing. We will examine how sliding windows can help address these challenges. One of the key considerations when implementing sliding windows is finding the right balance between window size and model latency. The size of the window directly impacts the amount of data the model processes at any given time. A larger window can capture more context, potentially improving model accuracy, but it also increases computational load and latency. Conversely, a smaller window might reduce latency, but at the cost of missing out on important contextual information. To achieve optimal performance, it is essential to configure the window size such that it maximizes throughput without significantly impacting latency. This involves analyzing the specific requirements of your application and experimenting with different window sizes to find the best configuration. We'll look at practical examples to understand these trade-offs better.
To enhance the efficiency of sliding windows, adaptive resizing techniques can be employed. These techniques involve dynamically adjusting the window size based on real-time data and model performance. By implementing feedback loops, the system can monitor its own performance and make necessary adjustments to improve throughput and accuracy. Real-time monitoring plays a crucial role in this process, as it provides the data needed to make informed decisions about window resizing. Algorithmic approaches, such as machine learning models or heuristic methods, can be employed to predict optimal window sizes under varying conditions. The main benefit of adaptive resizing is that it allows the sliding window to adjust to changes in data velocity and variability, ensuring that the model remains efficient and effective throughout different scenarios.
Window overlap is another critical factor that can influence the accuracy of a model. Overlapping windows allow for repeated processing of data segments, which can enhance the model's understanding of context and improve the accuracy of predictions. However, too much overlap can introduce redundancy, unnecessarily increasing computational load without significant gains in performance. To leverage the benefits of overlap, it is essential to determine the optimal overlap strategy that maximizes accuracy while minimizing redundancy. Case studies from various real-world applications demonstrate how carefully calibrated overlap strategies can lead to substantial improvements in model performance, providing a deeper insight into data streams and enhancing prediction quality. Sliding window mechanisms are particularly valuable in applications such as live chat and voice assistants, where real-time processing is crucial. In live chat, sliding windows help maintain the flow of conversation by ensuring that the model can process and respond to user inputs promptly. This enhances the user experience by providing timely and relevant responses. Similarly, in voice assistants, sliding windows allow the model to continuously process audio input, maintaining context and delivering accurate responses. The key to successful implementation in these applications lies in configuring the sliding window to balance speed and accuracy, ensuring seamless interaction. We will explore practical tips for integrating sliding windows into these systems, highlighting the improvements in user experience and system efficiency.
Measuring the performance improvements brought about by sliding window optimization requires a comprehensive evaluation strategy. Key metrics such as processing speed, latency, accuracy, and resource utilization should be tracked to assess the impact of optimizations. Establishing performance benchmarks helps in comparing the current performance against the desired outcomes. Integrating user feedback is vital for understanding the real-world effectiveness of the model, providing insights into areas needing improvement. Adopting continuous improvement cycles, where performance is regularly reviewed and refined, ensures that the model remains efficient over time. Success stories from organizations that have implemented these strategies showcase the tangible benefits and encourage the adoption of similar practices. Implementing sliding windows in real-time applications is facilitated by a variety of tools and libraries designed to simplify the process. Popular libraries such as TensorFlow and PyTorch offer modules and functions that support sliding window implementations, providing flexibility and ease of integration with existing systems. The ease of use of these tools is enhanced by extensive community support, offering tutorials, forums, and documentation to aid developers in the implementation process. Additionally, ongoing advancements in these libraries continue to introduce new features and improvements, ensuring that they remain at the forefront of technology. Choosing the right tools and libraries is crucial for optimizing sliding windows effectively, and we will explore the options available to help you make informed decisions.
As we conclude this session, it's important to reiterate the key concepts of optimizing sliding windows for real-time large language models. The sliding window mechanism is pivotal in managing continuous data streams, enhancing model efficiency and accuracy. Through optimization techniques such as adaptive resizing and careful overlap management, significant performance improvements can be achieved. These optimizations are not only theoretical but also have practical applications in enhancing user experiences in live chat and voice assistants. As technology evolves, staying informed about the latest advancements and continuously refining your approach will ensure that your models remain cutting edge. We encourage you to apply these concepts in your projects and explore the potential of sliding windows in your real-time applications.